The world generates 2 billion tons of organic waste every year. Most of it rots, releasing methane directly into the atmosphere. But engineers have built sealed steel tanks that capture that process, turning garbage into pipeline-grade fuel. Biogas is primarily methane and carbon dioxide. The methane fraction, depending on the waste going in, ranges from 50 to 75% of total gas volume. That range is worth millions of dollars annually to a commercial plant operator. The global biogas and biomethane market was worth $88.9 billion in 2024. Only 5% of the world's sustainable biogas potential is currently being used. Denmark already meets 35% of its national gas demand from biogas. Anaerobic digestion happens in 4 biological stages. First, hydrolysis. Complex polymers are broken down into simpler molecules by enzymes. Second, acetogenesis. Bacteria convert those molecules into volatile fatty acids. The process happens entirely without oxygen, inside sealed tanks. Third comes acetogenesis. Volatile fatty acids are converted to acetic acid, hydrogen, and carbon dioxide by syntrophic bacteria. Fourth is methanogenesis, where archaea convert these compounds into methane. These 4 stages take 15 to 30 days inside a mesophilic digester. 2 temperature regimes dominate commercial biogas production. Mesophilic digesters operate at 35 to 37 degrees Celsius, slower but more stable. Thermophilic digesters run at 50 to 55 degrees, faster digestion, higher throughput, but requiring more external heat energy input. The continuous stirred tank reactor, CSTR, is the most common digester design worldwide. A sealed, insulated cylinder with slow-turning internal mixers, it handles wet feedstocks at 8 to 15% dry matter content with reliable performance. The methane yield of any feedstock is determined by its biochemical composition. Lipids yield 1.0 cubic meters of methane per kilogram of volatile solids destroyed. Proteins yield 0.6. Carbohydrates yield only 0.38. Fats are 2.6 times more energy dense than starch. The reason lipids dominate is their hydrogen-to-carbon ratio. Fats contain far more hydrogen atoms per carbon than carbohydrates or proteins. Since methane is CH4, 1 carbon and 4 hydrogens, hydrogen-rich feedstocks produce more methane molecules per gram of organic material. However, high lipid feedstocks carry a serious operational risk. When fat concentrations exceed 3 to 5 grams per liter, long-chain fatty acids accumulate and become toxic to methanogenic archaea, the microorganisms responsible for the final methane-producing step of the process. This is why feedstock blending exists. No single waste stream is optimal alone. The art of biogas engineering is calibrating the mixture, balancing energy density against process stability and yield against operational risk. Commercial food waste, separated at source from restaurants, food manufacturers, and supermarkets, is the highest yielding practical feedstock in biogas engineering. It produces 100 to 200 cubic meters of biogas per ton, with methane content reaching 60 to 70%. Within food waste, lipid-rich fractions dramatically outperform others. Meat and dairy fractions yield 337 milliliters of methane per gram of COD, nearly double the 171 milliliters produced by vegetable and grain fractions. The cut of food waste matters as much as the quantity. Used cooking oil and slaughterhouse fats are the highest value biogas feedstocks in existence. UCO fed directly to a digester can push methane content above 70%. A ton of UCO produces significantly more energy than a ton of any other common organic waste. However, food waste alone creates an unstable digester. The high organic load acidifies the system rapidly, as volatile fatty acids accumulate faster than methanogens can consume them. pH drops below 6.5, and the microbial community collapses in a process called souring. To manage food waste safely, operators use two-stage digestion. A hydrolysis tank pre-acidifies the waste at low pH, then feeds a stable methanogenic digester. The process separates and controls each biological stage independently. Livestock manure is the backbone of agricultural biogas worldwide. Dairy cow manure yields 200 to 300 liters of biogas per kilogram of volatile solids, with 55 to 60% methane. Lower than food waste, but nearly impossible to destabilize. The reason manure is so easy to digest is that it already contains the right microbial community. Livestock digestive systems have pre-enriched the material with anaerobic bacteria and archaea. No inoculation, no seed sludge. The process starts reliably from day one. Manure's weakness is its water content. At 90 to 95% moisture, enormous volumes must be processed to extract modest gas yields. The digester volume required per unit of energy is significantly higher than for concentrated food waste. Agricultural residues represent the largest untapped biogas potential on Earth. 75% of total global biogas resource is from crop residues and straw. But corn stover, wheat straw, and rice husks are protected by crystalline cellulose and lignin that bacteria cannot easily penetrate. To make straw digestible, engineers apply thermal, chemical, or mechanical pre-treatment. Steam explosion. Heating straw to 180 to 200 degrees at high pressure, then rapidly releasing it, ruptures the crystalline structure, making cellulose accessible to hydrolytic enzymes. The energy cost of pre-treatment is the fundamental engineering challenge. In the worst cases, the energy consumed crushing, heating, and chemically treating straw approaches or exceeds the energy recovered as methane. The net energy balance becomes marginal. Municipal sewage sludge from wastewater treatment plants is one of the most underutilized biogas feedstocks in the world. Primary and secondary sludge yields 55 to 65% methane, and the feedstock is delivered free of charge. It is a waste product the utility must dispose of. Slaughterhouse waste and rendering plant outputs contain some of the richest lipid concentrations available to biogas operators. Blood meal, paunch content, and animal fats are routinely co-digested with sewage sludge at municipal plants, significantly boosting methane production. Biogas upgrading transforms raw biogas into biomethane, grid-quality renewable natural gas. Membrane separation units or pressure swing adsorption columns strip carbon dioxide and hydrogen sulfide, raising methane content from 55 to 65% raw biogas to 97% pipeline standard. Co-digestion of source-separated food waste with livestock manure is the proven optimal combination. Food waste delivers the lipid and protein energy density. Manure provides the natural bacterial consortium and buffering capacity. Studies show co-digestion produces 26% more methane than the sum of individual digestions. A well-engineered co-digestion plant running at optimum blend ratio can achieve 65% methane content with a hydraulic retention time of 20 days, generating enough electricity from a 1,000 cubic meter digester to power 500 homes continuously. The economics become compelling at scale. Is co-digestion the final answer? Or will new pre-treatment technologies eventually make lignocellulosic straw the dominant feedstock, unlocking that 75% of untapped global potential? Subscribe, because when commercial cellulosic biogas plants scale in 2027, we will cover every number.